Hello, my name is Ofer Elior. I teach programming at the Hebrew University of Jerusalem. In this video, I will talk about introductory programming studies. In other words, programming studies for beginners. More specifically, I will address this question: how should you start learning programming in the age of artificial intelligence? The question has been on my mind for about 3 years now, as a teacher and also in research. For about 3 years, I have been seeing how beginners use large language models, for example, ChatGPT, Google Gemini, and so on. Here, I will simply call them language models or models. Alongside watching how students use models, I also examine reactions to this, reactions among teachers, among researchers, and in the industry. In this video, I will explain how I see the question today. The date is early March 2026. What is then the right way for beginners to learn programming now? My discussion has three parts. First, I will say a few words about how programming changed. This change followed the arrival of models into our lives at the end of 2022. Then I will address a key question: do we still need to learn how to write code independently? In the third part, which is the main part, I will argue something else. When learning programming, we should give a central place to programming thinking, or if you prefer, computational thinking, maybe even more central than it used to be. Everything I say here depends on one basic assumption. The assumption is that we still need human programmers. As far as I know, in early March 2026, this is still true. So the question remains valid. How should humans start learning programming? My starting point is this: models, large language models, changed the act of programming in important ways. Most viewers probably already know this, so I will describe the changes very briefly. Before large language models came to our lives, when we wanted to solve a programming problem, the process was roughly this. Step one, we read the problem and understood it and designed a preliminary solution. For example, we were given a spreadsheet of employees in a factory, ID, first name, last name, gender, department A, B, C, D, and so forth, salary, and we needed to find how many employees there are in each department. So we planned a preliminary solution. Among other things, we thought about an algorithm that is a sequence of steps that solves the problem. We also decomposed the problem into smaller problems, and we considered other aspects of planning. Step two, we went to a development environment that is software where we write programs. For example, Anaconda Spider or Eclipse or Visual Studio. Based on our plan, we wrote an initial program. This program was the first solution to the problem. Step three, we tested that initial implementation, debugged it, improved it, refined it, and so on and so forth. Models, large language models, change this multi-step process I just described. They especially changed step two. Already in the early days of using models, we could solve problems differently. This was mainly about producing the initial implementation. That is, after planning the solution, we no longer went, or at least we were able not to go straight to a development environment. Instead, we formulated a prompt. In the prompt, we ask a model to generate an initial solution for us. So if we return to the example of employee frequencies by department at the beginning of the LLMs era, after the planning step, we did not go to an IDE, a development environment. Instead, we wrote a prompt. For example, the prompt shown here. Write a Python function named frex by department. We describe here the input, the operation of the function, its output, and then we have a prompt, a proper prompt. What we do now, after writing the prompt, we went to the LLM with that prompt. We entered it into a model. we received a proposed answer. Suppose it was this answer, we try to understand it. Of course, we have to understand it first, and then we move to the stage of testing and refining the solution the model proposed. From all this, we got a process like the one shown in this diagram. Phase 1, understanding the given problem and planning an initial solution. Phase 2, writing a prompt. Phase 3, obtaining a large language model's response to that prompt. Phase 4, understanding the LLM's answer. And Phase 5, iteration, namely a conversation with the large language model with the aim of debugging and refining and developing or perhaps generalizing the solution. Recently, even the process I just described has changed. Today, using models for programming is much more complex than I described. Programmers increasingly use what are called AI agents. That is, computerized tools which are based on large language models and are responsible to various aspects of programming. And your role as a programmer is mainly to orchestrate. That is the term, to orchestrate. You orchestrate the agent's work so they do the job, the programming job correctly. So these are the changes models created in programming work, and this is probably not the end of the story. There will likely be more changes in the future. And the question that interests me here is this: how should these changes affect the way beginners learn programming? Let's start with one of the hardest and most sensitive issues in this question. It is the teaching of independent code writing. Traditional programming courses always had a main goal. The goal was to give students the ability to solve programming problems entirely on their own, from start to finish. Meaning, if you are given the problem I showed earlier, a programmer should be able to write a solution alone, without models and without any external help. And this approach was manifested in home assignments, in final exams. These were all filled with write a program that, write a function that, write. Do we still need this today? After all, models can supposedly generate all the code by themselves. And maybe all we need as programmers is to read and explain model-generated code, not to write code. So we must admit that the claim that we no longer need independent code writing is legitimate today. No, definitely not all programming learners need to program independently. I will not enter here into a discussion of the many tools and methods that exist today. Tools that allow you to generate code without knowing how to write code. This exists. It is a fact, it is possible, it is familiar, it is well known. I have nothing to add on that point. It is a real fact that today programming can be done without knowing how to write code. And I will note here that there are already textbooks on the market that take exactly this approach. They teach programming with the help of models. And they do not set independent code writing as a goal, at least not as a primary goal. On this slide, you can see one of these more popular books. In addition, this approach is starting to enter academic programming courses. In any case, after saying all that, I still want to say something important. To beginners and future beginners who are watching this video, you must be aware of a crucial point. Knowing how to write code independently without help from models will give you a depth of understanding you will not get if you only know how to read code. What do I mean by depth of understanding? Depth of understanding means you master several abilities. These abilities can be critical in programming work. The ability to predict a program's output before running it. The ability to explain a program, its components, its edge cases, and the design it is based on. The ability to make small local fixes without changing the whole algorithm. The ability to generalize, that is, to write a general solution, a solution that handles not only one specific problem, but a family of similar problems. I will talk about this again in a moment. The ability to design test cases independently, test cases that reveal errors in code that looks correct. You may very well possess these abilities to some extent if you only know to read code, but you can really master them if you know how to write code independently. So, if you are starting to learn programming, you should be aware that you are at a crossroads. You need to decide whether you want this depth or not. As I said, it is completely legitimate to say no. Maybe you do not need it in the specific context where you expect to program. But if you choose to invest and to learn independent code writing, I strongly recommend that you set for yourself what we might call a protected foundation phase. This is an initial period of learning. In this period, you greatly limit your use of large language models. I know this is not a popular suggestion, and I understand that many will find it hard to follow. I do not suggest it out of nostalgia and not of blindness to what is happening in reality. I suggest it mainly because a period of learning with little or no model use builds an important ability. It builds the ability to create, not only the ability to read or to evaluate code. In slightly more professional terms, such a period builds a mental model. This is needed if you want to understand deeper code issues later in your learning. Many students come and tell me, Professor, I understand everything you are teaching us during lessons, but when I come to answer questions in the home assignment, I do not know how to begin answering, and I get frustrated. Of course, I do not ask the model to solve the question for me. I only ask it to give me a direction, a beginning. When I hear that, I am myself deeply frustrated. Yes, in that protected foundation period, you can use AI to help with things like dealing with the development environment. And you can use it to explain unclear error messages, and even to fix simple syntax errors like missing parentheses. But frustration that comes from having to derive the logic of a solution, from choosing an appropriate data structure, from decomposing a problem, and from other aspects of thinking and solution development, that frustration is good frustration. It builds what we can call the internal processor. If you avoid it by turning to a large language model, you collapse the learning process before it is completed. It is also worth saying that independent code writing will become rarer, and therefore it will also become more valuable. If you achieve this depth, you may gain an advantage compared to other programmers, and especially in the eyes of at least some employers, because there are still employers who see value in this. They want their programmers to know how to write code themselves. And it is exactly because independent code writing gives a depth of understanding. In critical moments, in crisis situations, and also in normal routine, there is an important advantage to the deeper understanding that independent code writing creates. If I use an analogy, in these respects, programmers are like pilots. An airplane can fly automatically, and yet pilots learn to fly manually. And that is, of course, critical in emergencies. When the system does not behave as we expect, it is necessary that someone diagnoses what is wrong and limits the faulty activity. In the same way, programmers with deep understanding can function even in situations where models are not helpful. For example, when models were not trained on information relevant to the problem. Such programmers can also take responsibility for correct logic, and for the ethics of the code that models produce. So that was the issue of independent code writing. Now I will move to a broader question. What should programming learning focus on today? Let's look at the code snippet shown here. This is a code solution to the earlier problem. computing frequencies by department. What do you need to know to write this code? Or alternatively, what do you need to know to understand it? If we assume a model generated it. To understand this code snippet, like any code snippet, you need to know programming fundamentals, the building blocks of the entire field of programming. What are values? What are variables? What are arithmetic operations? What are strings? What are conditional statements and conditional structures? What are loops? What are functions, user-defined functions in particular? And also, and this is extremely important, what are data structures? These are basic concepts in programming, and every high-level programming language has them or is based on them, at least most of them. These are still the bread and butter of the field, and they are still taught in programming courses and intro textbooks. There is no way around it. This is a must. Beyond fundamentals, you also need what we can call a technical toolkit. I mainly mean specific functions or operators or libraries of functions, for example, the function print, or the library of functions pandas. Clearly, to write the code shown here, or to understand it, if a model generated it, print and pandas are not part of programming fundamentals. Yet, you need to have print and pandas in your technical toolkit in order to either write or understand this code. Courses and textbooks cover many parts of the basic toolkit, but of course not everything. In your ongoing work, you will need to fill gaps when needed, learn certain functions and libraries. You can do that using large language models, forums in the internet, and so on. So we discussed the need to understand fundamentals and the need to know, to have and to know a technical toolkit. But, and here I reach the main point, there is something more. There is another important thing you should know when you write code or understand code produced by a model. What is it? It is computational thinking. That means understanding how the computer thinks, or for our purposes, how the model thinks, specifically when it generates code. What do I mean? Let's start with this. One thing beginners do not always understand is what experienced programmers see in code. They see something beyond one function or another, beyond one structure or another. They immediately see the thinking behind the code. Here, when they see the lines highlighted in yellow, they immediately recognize that this code is based on a certain pattern, a pattern that many programs are based on. Specifically, this pattern, a way of organizing a code, is called a frequency dictionary pattern in Python. Never mind the name here. The idea is that this way of organizing a code is very common. Many programs are based on this pattern, as said, and it itself is one of many other programming patterns. We want to know these patterns because they help us grasp faster and better the thinking behind model-generated code, and of course, writing code ourselves if we do that. And more than that, computational thinking is not only code patterns. Computational thinking includes many other skills. I will mention three more very briefly. One skill is choosing the right data structure efficiently. Suppose you are told, read all the data in our employee file, the one we saw earlier, and perform these actions. Find employee frequency by department, compute the average salary, create a spreadsheet that contains only the rows for women. Before we even perform these actions, we must answer a basic question. How should we store the data from the file so we can do these operations? When I say how, I mean what data structure should we use? High-level languages like Java, C++, and Python offer more than one way to store data. For example, Python offers list and dictionary and other structures. And the question is, which data structure, which way of organizing the data best fits the problem. Understanding how to answer this question is a computational thinking skill, and it is very important to acquire it. It is especially important in the planning stage, the first stage, because correct data representation saves many problems later. And again, that is not a technical skill, it is a thinking skill, a very important thinking skill. Another computational thinking skill that is mainly important in planning is decomposition. That is knowing how to split a problem into sub-problems. This is mainly about complex problems, real-world problems. For example, let's look at this problem. You need to write a program that manages a chocolate shop. This is big and complex. The skill is knowing how to divide the large problem into smaller problems. For example, a sub-problem for handling customer data, a sub-problem for handling employee salaries, a sub-problem for handling supplier orders, and more than that. Each sub-problem may be decomposed further. For example, the sub-problem that handles customer data can be decomposed into 1, 2, 3, 4 sub-problems itself. Solving each of these sub-problems is much easier than solving the original big problem. And after we solve each of these problems, we combine all solutions into a solution to the big original problem. And the point is that decomposition is again not a technical skill, it is a thinking skill, and possessing it make your programming much more efficient and robust. A third and final example, the skill of generalization. Let us look at this problem. You need to write a program that produces driving directions, say, from the central bus station to the dentist. So, no problem, that's quite easy. We just print an explanation to the screen, something like, leave the central bus station, turn right on street A, continue 300 meters, turn left, arrive at the building, and finally go up to the 5th floor. Programmers can write a program that outputs these directions, but they will not do that. Why? Because programmers usually do not settle for a solution to one concrete case. It is not efficient. For example, they will not want to write a separate program for someone who wants to drive from the courthouse to the beach, or from the beach to the dentist, or from the beach to the courthouse. And this is where generalization comes in. As programmers, we aim to write programs that solve many similar problems. Such a program is based on identifying what is common across these problems, and also what changes from one problem to another. For example, here every program starts at some starting point and ends at some destination. Every program has 0 or more intermediate stops, and the instructions come from a fixed set of instructions. For example, left, right, go up the stairs, and so on and so forth. Once we identify the shared components and the changing components, we can write a more general program, a program that works not only for one specific case, but for many. Again, a very important thinking skill, generalization. So what is the lesson I suggest taking from this discussion of computational thinking if you are a beginner in programming? The lesson is this: programming is not only technique, and it is not only the use of models. Even though today it may look that way at first glance, programming is thinking, computational thinking. If you want to be good programmers, and even if you will not program as a profession, you must try as much as possible to develop computational thinking. Furthermore, computational thinking is critical when using AI agents for programming. That orchestration I mentioned earlier, managing AI agents to program, requires programmers to act like architects. Architects can decompose a problem into subproblems. They can assign a specific sub program to a suitable agent, and they can verify correctness. In effect, AI gets the role of the how, and programmers are responsible for the what and the why, defining the problem, decomposing it, and judging correctness. All of that is based on computational thinking. In parentheses, I will note that unfortunately, programming courses and textbooks do not always emphasize these topics. Topics like decomposition, generalization. Often, they focus mainly on fundamentals and the technical toolkit. If that is your situation, if your course does not discuss these topics, or if you use books that do not address computational thinking, I strongly recommend that you fill the gap. You can use models, large language models, although honestly, I'm not sure they are already a good tool for learning computational thinking. In any case, there are books, and here I mentioned two of them. And since we are already talking about textbooks, I need to mention something else. As I have said, there are already programming textbooks that focus on programming with models, like the popular book shown here. One important thing to be aware of if you use these books, or at least the ones I have seen, is this. They either assume you already control the fundamentals and the basic toolkit, or they teach them but not systematically. In other words, they are different from traditional programming textbooks. Traditional books taught a programming language thoroughly and systematically. In that sense, these newer books make an important an assumption about the reader's prior knowledge, or about the reader's ability to understand important topics, even when they are not taught in a systematic way. This is something you should think about. I will end by describing what I would do if I were starting to learn programming today. I would begin with an introductory course, or with good textbooks, books that I know teach computational thinking, not only fundamentals and toolkit. During the learning process, I would avoid using models entirely, at least until after I learned the programming fundamentals that I listed earlier. In addition, I would learn to write code independently, again, at least at the level of fundamentals. I would do this because I would want deeper understanding of programming thinking, computational thinking. As I said, I would define in advance a limitation period for model use. I would define it by learning topics, and maybe I would even define it by hours. For example, the first 40 hours of learning or the first 60 hours. Only after completing this learning phase would I move on to specializing in using AI agents for programming. So that's it. Good luck to everyone who is starting to learn programming. And of course, I will be happy to receive responses and comments.